Okay, let's start. So turn on video. So we have a little fewer students. And I will be posting the midterm one, I mean the take-home midterm on Friday. But you will have 1 week after the fall break is over, so you will have a little more than 1 week. So I can wait until next Wednesday, but I think it's no point. Maybe some of you want to start faster, or some of you want have some plan, and they can start after the fall break. Okay, and if you got a reasonable score in midterm, then you will be fine to finish the course at least. And of course, you have a final project and you have other homework and quizzes. But usually, if you are successful in your midterm, then you will be successful in the course. As long as you made a reasonably good presentation. Yeah. So if you're thinking about, the dropping the course or something, then yeah, certainly after midterm you can decide, and also I will make some recommendation. Okay, and do you have any questions on quizzes or any other materials? Okay. Chapter 6 is really important chapter, and probably the most applications. And chapter 11 as well. Chapter 6 and 11 are most important chapters. So I would like to just review the previous lecture quickly, then go on to the next material. And after that, we are thinking to do exercise 7, problem 2, hopefully. So we are doing regression right now in chapter 6, and the situation is here. So we have x and y, and the x and y are observed, and we want to explain y by x. And our model is y is a linear function of x plus some error. So this is probably the simplest possible relationship between x and y. And in practice, the relationship is not this easy, but the statistics is just an approximation method. So that we explain y by x, then plus some errors. Yeah, so error is an important concept in statistics, right? So for example, maybe the physicist or maybe medical doctors assume that the people's ability is determined by genes and environmental factors, but the statisticians probably decompose it into gene factor and environmental factor and an error, because not all gene factors and not all environmental factors are factored in the data usually. And our objective in statistics is to estimate this A and B. So we want to specify the intercept and the slope of this relationship. Yeah, so that is the case. So x and y are observed. X and y are observed, and the AB and epsilon are not observed. And our objective is to estimate AB. And as a result, we can also estimate epsilon. And those are written as A hat, B hat, and epsilon hat. Yeah, and usually we estimate the fitted line A plus BX by minimizing the sum of squared errors, epsilon i's. So this is, statistically speaking, the maximum likelihood estimator. So it's kind of the best estimator in some statistical sense if epsilon is normal and IID errors. So basically, we minimize the sum of squared, the deviations of observations to determine the light blue line. And yeah, we have some formula to calculate A hat and B hat. And this is one example of the fitting Y on X. And yeah, we can use LM function to do linear regression. So if price is Y and the square footage of the house is X, then if we want to fit the Y on X, that means the Y is equal to A plus BX, then we have to use this LM function to fit the data. And once you fit the data, so remember that this price and square footage is a data set. So maybe if we have 100 observations, the price is a vector of 100 elements, and the square footage is also the vector of 100 elements. And here we attached the data, and we write just the price and the square footage, since these two variables are within this data set. Actually, another notation, a possible notation, is LM. Sorry, LM, the price over square footage, and you can specify data is equal to this data. So our data is here. So even without attaching the data set, even without this line, still if you specify data, then you can fit the linear model. So this is another way to specify data. And you can get intercept A hat and the B hat, the slope B hat. Yeah, and the residuals is defined by Y minus A hat plus B hat X. Maybe residual here. So this is the estimated epsilon. Often we assume epsilon is IID normal. So to check this assumption, we have to calculate the epsilon hat. And this is also another important slide. So we have matrix representation of linear model. If we have n observations, basically we have n different equations. So it's pretty natural to make a matrix representation. If you define the y as a vector of y1 to yn, and if we define x as a matrix of vector of ones and the vector of x1 to xn, and define beta as vector of a and b, and epsilon as this, we can write the model as y is equal to x beta plus epsilon. And how to estimate a hat and b hat, I mean, how to estimate a and b. So those are actually summarized by just one equation here. So beta hat. Beta hat is x transpose x inverse times x transpose y. So x transpose is just, if we have x is ABCD, x transpose is the other way around. So if we have original matrix ABCD, then transpose of this is ACBD. Yeah, and we proved it, and the proof is pretty simple because the squared errors is minimizing some quadratic function, and the quadratic function is pretty easy to minimize. You can see that if we have maybe univariate case, f of x is x squared minus 4x plus 2, which x minimize this function, then we can just differentiate it. That becomes 2x minus 4. Then we can equate to 0. Then we can say x is equal to 2 is the minimizer. And even if we have two variables, a and b here, still we can do the same thing. So we differentiate this function, the sum of squared deviations, by a and b, and to solve some linear equation, then we can get this beta hat. This is a pair of a hat and b hat as this. Yeah, so if we just use this formula, we define y and x matrix, then if we write this way, then we can get the a hat and b hat, the same answers as above. So remember that the solve is inverse, and T of x is transposed, the x transpose, and this is matrix product. And yeah, this is the definition of residuals. Residuals also have vector form. Then today's topic. Today's topic is several things, but the first one is the variability of beta hat. So we estimate A hat and B hat, but that depends on data. So if we have x-axis here and y-axis here, and we have, suppose, the 5 observations, then we can fit the data like this. But if we have another 5 observations with the same population, then okay, so maybe even if these observations are similar, still the fitted line is slightly different, right? So that means we have different A hat. Maybe the first A hat is here, and the slope is B hat. But the red one, A hat, is slightly larger, but probably the slope B hat is slightly smaller. So A hat and B hat have some variability. So we want to see the how much variability A hat has, and also how much variability B hat has, and also what's the relationship between A hat and B hat. If A hat is larger, then B hat is smaller, or B hat is also larger. We want to know those pieces of information. So, yeah. So probabilistically, in terms of probability theory, okay, so beta hat is given by this, and the y is equal to x beta plus epsilon. That is the linear model. And epsilon is a random variable. I mean, random vector to be exact. So actually, if we expand this equation, you can see this is beta x transpose x inverse x transpose x. That cancels. So just we have beta here, then times x transpose x inverse x transpose epsilon. So we have this. And this is actually random because epsilon is random. The beta is, the true parameter. So true parameter plus some kind of noise that caused by epsilon. So that is the probabilistic interpretation of beta hat. So we want to see how this beta hat behaves. So how epsilon affects the estimated A and B. So this beta is actually the exact pair of A and B, but we have some disturbance here. And the theorem, this theorem gives the variance of beta hat. So variance of beta hat means the covariance matrix of beta hat. Some people say variance covariance matrix of beta hat. So that is the 1-1 entry or 1-1 element is variance of A hat, or you can say this is covariance of A hat and A hat. So this special covariance is called variance. And the diagonal element, the 2-2 element is variance of B hat. And off-diagonal element is covariance of A hat and B hat. So basically, we are thinking about the row of A hat and B hat and the column of A hat and B hat, and we combine this to represent all the variance of A hat and variance of B hat and covariance of A hat and B hat. And actually, these 4 quantities are just obtained by one formula. So variance of beta hat is 2x2 matrix, but actually this is sigma square, that is the variance of epsilon i's. Actually, this should be estimated as well, times x transpose x. Remember that x is n by 2. So x transpose is 2 by n. So entire quantity is 2 by 2. So 2 by 2 matrix. So we have inverse of that. So we take inverse. So this is 2 by 2 matrix. So 2 by 2 matrix times this, number, the scalar. So we can get this 2 by 2 matrix. And sigma square is not observed. even if epsilon is not observed, so sigma square is not observed. So we substitute this by this kind of the sample version of sigma square. So epsilon has mean 0. So basically the expectation of epsilon I square is variance of epsilon I square. So variance is, approximated by sample variance. So 1 over n minus 1 times, the variable, the square of variables, sum of square of variables. But here, actually, the epsilon I hat is calculated by yi minus a times a minus b times xi, okay? Maybe a hat times b hat. Yeah. And here, a hat and b hat are both unknown quantities, and these are estimated. So basically, that lose basically 2 pieces of information. So that is reflected by here. So usually when we calculate variance, the variance of x1 to xn is calculated by 1 over n minus 1 times summation xi minus x bar square. And the why n minus 1? Basically because we replace the true mean mu by x bar. So we lose we substitute one of the information. So that's why that we put the n minus 1. And here we lose 2 pieces of information, a hat and b hat. So we substitute this by a hat and we substitute a and b by a hat and b hat. So that's why we put 2. I don't exactly explain that, but basically, if we use a hat and b hat, the size of epsilon I square, absolute size of epsilon I square is underestimated. So we need some adjustment term, -2 here. So we can calculate the sigma hat, but we can estimate sigma hat by this quantity. So this is estimate of sigma, so sigma hat square. So this times x prime x. X prime x is known matrix, so that we can calculate this, then inverse. So we can calculate this variance of beta hat. I got 2 questions, sorry, I missed it. The first question, how would we know that the epsilon i's are independent? Yeah, we will see it later. Yeah, basically we use residual plot. We see the residuals by several other criterion. Yeah. And the second question, in R, if we were given x is equal to 1 to n as a vector, does that imply that x is a transpose matrix, or we have to take the transpose of x? Yeah, so maybe I have to write. So the question is, when we are given 1, 2, n transpose, yeah, that means x is column vector. Yeah. So yeah, so x is a column vector. That is the answer. So x is the yeah, so vector is a special case of matrix. So we can say that this is the transposed 1 by n matrix. Yeah, in mathematics, often we define x as this, and in the sentence we have the x transpose. So actually the x transpose is row vector, but that is also possible. Yeah. The column vector is hard to define in the, the textbook, I mean, in the sentence, right? So because we are using, the horizontal lines to write the letters. So that's why it's easier to define row vectors. But if you want to define column vector in the sentence, sometimes you use the transpose symbol. Yeah, that's why that we often see transpose symbol, even though just, we can define the column vector directly. Yep. And third question, why does R give me a row matrix if I take the transpose of a vector? That's very good question. So R does not distinguish row vector and column vector. This is mathematically very strange, but just R works in that way. So if you define, sorry, what happened? Yeah, if we define the two vectors in R, the A is like the C12 and B is like the C34. It sounds like both are column vectors or something, but actually you can calculate the a matrix product, sorry, a matrix product of matrix product. Yeah, I think probably we can still do that. And this is interpreted as 1, 2, 3, 4. I believe so. Yeah, just because R works this way because it's probably more convenient practically. So logically, it does not make any sense, but yeah, that's the reason. I can double check it. Yeah. Yeah, actually it works in that way. Yeah. So actually you don't have to transpose vector in any case. Even you make a mistake, R automatically interprets as correct statement by making A is a row vector or a column vector. Okay, and now that we want to prove this, the variance of beta hat is equal to sigma square times X transpose X inverse. And yeah, variance of beta hat. Okay, so variance of beta hat is variance of this. Because the variance of beta hat is, okay, so beta hat is equal to beta plus X transpose X inverse X transpose epsilon in the previous page we see. But the beta is constant. So constant term does not matter for the variance. Generally speaking, the variance of X plus C, if C is constant, this is variance of X. So beta is dropped. And the variance of X transpose, X inverse X transpose, Y, epsilon. And this is actually equal to this one. So at first, the yeah, so the variance of this, and yeah, generally the variance of some vector, I mean variance covariance matrix of this vector is equal to the E times the V transpose. Then you can just verify it by writing everything by element. So suppose V is 2 by 2 matrix, and we have the 4 factors, and sorry, the V is the two-dimensional vector, like the x1 and x2 or something. And then if you write the both expressions, you write down both expressions element by element, then you can see that these are the same. So, okay, so we have vector V here. So we have vector V here, and we have the V transpose. So in that way, then we can calculate the variance. And how to calculate this? Okay, so this is transpose, and remember that the AB transpose is equal to B transpose, A transpose in general. So we have 3 matrices here. So at first we transpose epsilon, and that comes here. And we transpose X transpose, that becomes X again. And we transpose X prime X inverse. And actually, that becomes X prime X inverse again. Y X prime X inverse transpose. This is actually the same. Yeah, so this is generally true in matrix algebra. Yeah. Maybe because, okay, so X transposed X inverse. Yeah, maybe we have originally this equality, right? So the X transpose X is one matrix. So the inverse of this times the original matrix becomes I. Then we transpose this. Then that becomes using this property, X transposed X transpose, right? And then X transposed X inverse transpose is equal to I. Right? But if you calculate this, we change the order of these two matrices and the transpose again. So actually this becomes X prime X. So that's why this quantity is inverse of it. So that's why we get X prime X inverse transposed is equal to X prime X inverse by definition, right? So because X transposed X times this yellow quantity is I. So this yellow quantity should be X prime X inverse by definition of inverse. Sorry, it's so complicated, but yeah. Anyway, so the matrix algebra makes it, okay, so this is just the original one here, here, and epsilon here. Oh, sorry, this is fine. And yeah, then X and X prime X inverse. Okay, that's it. And take expectation. But the basically this is constant, right? Constant matrix. X is constant. So only epsilon has randomness. So this is also constant. And expectation is linear operator. So we can take these quantities out of expectation. So generally, expectation of AX is equal to A times expectation of X if A is a constant. And this even applies for matrices, right? So that we can write this one times expectation of epsilon hat prime and times this one. And expectation of epsilon transpose. This is actually, epsilon is the vector of epsilon 1 to epsilon n, actually the column vector, right? So this is, epsilon 1 to epsilon n, and epsilon 1, epsilon 2, up to epsilon n. So this becomes actually the epsilon I epsilon j. I mean, the ij's element of this matrix is epsilon I epsilon j, expectation of epsilon I epsilon j. But this quantity is 0 if I is not equal to j, because independent. If independent, expectation decompose, and the expectation of epsilon I is 0. And if does not decompose, if I is equal to j, then just the expectation of epsilon I square. So that is sigma square. So diagonal terms are sigma square and off-diagonal terms are 0. So that makes this entire quantity as sigma square times identity matrix with degree n by n matrix. Then, okay, then basically I can be ignored, and the sigma square is just a scalar. So maybe we can sigma square the in front of the entire quantity. Then you can see that the remaining term is X prime X inverse times X prime X times X prime X inverse. But these yellow quantity cancel because this is some matrix inverse times that matrix. So it cancels. So only this second term remains. Then we get the sigma square times X transpose X inverse. Yeah. So identity matrix does not change any matrix. So we can ignore it. I to X is, for example, just X. So this is the end of the proof. So in this way, we can calculate it. Any questions so far? Oh, you can I got some comment. You can interchange the transpose and inverse. Yes, yeah. Okay, and using this fact that we can test the coefficient. So remember that the in chapter 5, we did t-test. That is, we observe x1 to xn, and we have population mean mu, and we have sample mean x bar, and we can test if the mu is equal to some specific number by using x bar, and that is t-test. And our test statistic was the x bar, x bar minus mu naught over standard deviation of x. So then this follows t-distribution, and we can do t-test. And we can do similar thing for estimate for A and B. So a situation in chapter 5 is basically, intercept model, right? So if we have x, then x has the mean mu. So that means x basically equals to mu plus epsilon. So we don't have any slope, but we only have intercept. And we test this intercept. And this time, x1 to xn, y1 to yn, we have the variable, and we have the x is equal to, sorry, y maybe. Y, we have actually the pair of n pair of random the data set, and the y is equal to a plus the b times x plus epsilon. And now we want to test this a and b. So we want to test if, for example, a is equal to 0 or not. So null hypothesis maybe a is equal to 0, or maybe null hypothesis is b is equal to 1, or something like that. So we want to test that kind of hypothesis. And we want to construct some relationship similar to chapter 5. And if epsilon follows normal, the 0 sigma square, and IID, that is a necessary assumption, then this quantity, a hat minus a. So this is a kind of similar to chapter 5. So x bar minus mu naught. X bar is, estimate for mu naught. Here, a hat is an estimate for a. So actually, so basically we are thinking about assumption that so if the true parameter, true intercept is a, then a hat minus a divided by standard error of a hat. That is that follows t-distribution with degrees of freedom n minus 2. So here 2 is a little different from t-test. T-test, we have n minus 1. But basically, since we estimate 2 parameters, basically we get 2 here. Standard error is basically the standard deviation. If this inside quantity is some estimate, then standard deviation is called standard error. So standard error is a kind of the special case of standard deviation. And a hat minus a over standard error of a hat, that follows t-distribution. So basically, if this quantity is large enough, then large enough in absolute value, that we conclude that the true parameter is not equal to a. Maybe we should put maybe a naught, that may be more appropriate symbol. We are thinking about the null hypothesis of a is equal to a naught. Then we calculate the t statistic. Then this quantity follows the t distribution under this null hypothesis. And for b, we do the same thing. So b hat minus our hypothetical value of b divided by standard error follows t distribution with degree of freedom n minus 2. Yeah, and standard errors is just the standard deviation. So if we take square root of variance, then we can get this. Yeah, with this theorem, that we can test if h naught such as a is equal to 0, or a is equal to a naught, or b is equal to 0, or b is equal to b naught. We can test this kind of hypothesis. Yeah, often we are interested in testing whether a or b is significantly different from 0. And sometimes b is equal to 1 is good hypothesis to test. For example, x and y are very similar variables. X is maybe the left lung volume of fever, and y is right lung volume of fever. Then we expect these are similar and y is approximately equal to x or something, but we want to test if this coefficient is really equal to 1. If estimated line is 0.01 plus 0.99x, we are often interested in this if this coefficient is close enough to 1. Yeah, and in terms of coding, we can just get all results by just getting a summary of LM1. So remember that the LM1 is a linear model, so we fit the price on square footage. Then if we put the summary function of this LM1, so linear model result object, then we can get these results. And you can see the t value here and the p value here. So basically this t value test if a is equal to 0, and the p value is very small. So that concludes that we reject h naught. So a is not equal to 0. How about b? B has the t value of the 6.2 and p value of less than 10 to the power negative 7. So suddenly we reject the hypothesis of b is equal to 0. So we have positive slope. So this means that we have one more square footage. Actually, the price is $0.2473 higher. So one more square footage, $247 you have to pay to buy the condominium. And yeah, we interpret these other numbers later. But this 46, this is n minus 2. So this is the degrees of freedom for the t statistic. So this means, so this implies the number of observations. How many observations here? N minus 2 is 46. So we have 48 observations. So with only seeing our linear model output, we can tell how many observations are there. So this is estimate for sigma, so sigma hat. So square root of variance of sigma. Sorry, the square root of the sigma hat square. And the adjusted r squared and r squared multiple r squared, I will explain it later. 0.45, 0.5. And this is the entire significance of this linear model, basically intercept and the slope combined. Sorry, I'm wrong. So this basically tests the same thing as this. And actually we have same p-value. Maybe we will discuss it later, how this is useful. Yeah, so yeah, we have, okay, so this is A hat, and this is B hat, and this is standard error of A hat, and this is standard error of B hat, and so on. And the error of A hat is calculated by square root of this, and the variance is, yeah, obtained by the method we discussed. And the square error of the standard error of B hat is equal to 0.0399. Yeah, and so if A is 0 and B is 0, then if A is 0, this follows t distribution with df46. If B is 0, this quantity follows t distribution with df46. So this is, B hat minus 0 over SE B hat. Yeah. So both A hat and B hat are significantly different from 0. The intercept usually doesn't have much meaning in many examples. So here, what is the meaning of this negative 265? That means if square footage is 0, then price is negative $265,000. It does not make much sense, but maybe you can, make up some story, like the condominium comes with property tax, also association fees. So if we have 0 square root, then that has negative value, and that is negative 365,000. But sometimes it's hard to interpret intercept. So often the most important quantity is this slope and the test result for slope. So they put intercept in parentheses, so it indicates it's slightly less important. Any questions so far? Yeah, I will check the attendance here. I think I can. Now I realize that my large monitor can screenshot all attendees. Okay. Yeah. And if you don't have questions, then we go to the next one. This is the coefficient of determination, or R-square value. So in the previous output, we see that the R-square is equal to 0.45, or adjusted R-square is equal to 0.44, slightly smaller number. And what does this mean? Definition of R-square value is actually 1 minus the sum of squared errors over sum of squared total. What are these quantities? The sum of square total at first. This is just the kind of variance, the variation in y. And the SS error is actually the variation of error. So the variation of epsilon i's. So that means if we have, so y bar is basically the the mean of y. So if we are allowed to use only intercept in the linear model, basically SS total explains the size of errors. And SS error is the error size when we are allowed to use intercept and also slope. So basically this means the error size for the model y is equal to a, and error size for the model y is equal to a plus bx. So that means, yeah. So for example, if SS total is 400 and the SS error is 100, then error has been reduced by 75%. So that means the variable x explains the 75% of variation in y. So basically this R square is the percentage of variation explained by x. So that is R square. So R square is between 0 and 1 and equal to 1, then basically x perfectly explains y. And if 0, then x is, garbage. X is not informative for y. X does not explain y at all. X doesn't have any explanation to y. X does not explain y at all. So that is the fact. And adjusted R square, this only makes sense if we extend this linear model, but if we want to define it, actually we only have difference here. So denominator is divided by n-1, numerator is divided by n-2. So that means the denominator gets, the numerator relatively gets smaller. Larger. So adjusted R square, entire quantity gets a little smaller. So this is actually the less than R square, slightly smaller. And we will interpolate this later in chapter 11 again. So for now, just you can see these are just similar quantities. And R square, actually, if you calculate the correlation between x and y, this is R, then actually this R square and R square are the same, even though we use lowercase for correlation and the uppercase for coefficient of determination. Yeah, so that is what I explained. Meaning of R square. SS total is total variation of Y. SS error is the variation of Y not explained by X. So hence R square represents how much variation of Y in terms of square deviations is explained by X. So if R square is 0.8, we can roughly say that X explains 80% of variation in Y. Yeah, and actually, if we have multiple predictors, such as we explain the blood pressure by the weight of people and age of people, height of people, and so on. If we have multiple variables, p variables, adjusted R square is defined by this SS error over n minus p minus 1 over this total. So the p affects here. So large p, denominator gets larger, numerator gets larger, and 1 minus entire quantity gets smaller. So adjusted square gets smaller. So p larger, then p gets larger, then adjusted R square gets smaller. So it's a kind of, we penalize the large p. If we have many variables, then we can explain why better, right? So obviously R square gets better. So we penalize the large p. So that is the concept of adjusted R square. So roughly speaking, if the true coefficient of an additional predictor is 0, then adjusted R square does not increase. So if we add redundant variables, or just one redundant variable, then even if it's not entirely useless, still, if we have just finite observations, like 10 observations, we can adjust the coefficient of that predictor to get explanatory, to explain why better, right? So R square gets slightly better. So we just want to avoid that situation, and that concept is, so adjusted R square is made for that concept. Any questions? Yeah, but anyway, so adjusted square, that we need to go to chapter 11 to exactly interpret it. Yeah, so remember that, so the one typical example of, sorry, maybe I just postpone the explanation to chapter 11. Okay, so yeah, so that's the explanation of outputs. Now that we have interpreted most output of LM function. And I think this is yeah, so the next one is the fitted values. So originally we have that y is equal to x beta plus epsilon, and now we estimated beta. So x beta hat is a kind of expected quantity of y. Actually, to be exact, expectation of y is equal to expectation of y is x beta hat approximately. So this is a kind of the predicted value of y, right? So we estimate beta, and epsilon is an error size. So if we remove error size, then basically we can calculate the expected, estimated value of y. So that is the called the fitted values, and that we can use the fitted function or fitted dot values to obtain those numbers. So this is LM object and $ fitted values. Then we can get the fitted values for first observation. So this is equal to basically A hat plus B hat times X1. And the third one is A hat plus B hat times X3 and so on. And the same quantity is obtained by fitted of LM1 or LM1 bracket 5. And residuals is epsilon hat. And this is obtained by the $ residual or resit of LM object or LM1 too. So in this way, this is basically epsilon 1 hat, epsilon 2 hat, and so on. And residual is used to see if linear model assumption, that is epsilon I follows IID normal sigma square. And these are residuals, so epsilon I hat, and this is square footage, so basically xi, and this is the plot. So basically the residual is around 0, so maybe it's good to have the horizontal line here. Then if assumption is satisfied, this graph should not have any pattern. So in that way, we can check if epsilons are IID. For example, this looks almost no pattern. This does not have any pattern almost, but we have some problem maybe around here. All of the errors are very small, maybe even including this. So that means if square footage is 3000, epsilon hat is large negative values. So epsilon hat is large negative values. That means what? If we compare yi and the a hat plus b hat xi, epsilon hat is very large negative value. So that means the yi is much less than this. So the model a plus bx, the overestimates the price. So maybe we have several condominiums of this, the size, whose condition is so bad. So that's why we have large negative error size here. So we have to subtract epsilon I hat to get the true price. So we have some problem here, but the mostly, maybe also the variation, the size of variation gets larger if the square footage gets larger. So that is another problem. So large square footage makes its residual larger. So we have two problems, but we have several other possibilities for residual plots. For example, if residual looks like this, obviously we have some pattern, right? So in this case, this is xi and epsilon I hat. It sounds that this is cubic function. So maybe we should put xi square and xi cube to explain y as well. Maybe some other curvature, clear curvature like this. Sorry, and actually the average size of error is adjusted to 0. So on average it's 0, but still we have some pattern. Yeah, so these are typical patterns. And how to, solve these problems? That is a question. And possible remedies is at first to transform both variables before regression. Sometimes we have to transform just x, just y. So, the variation is larger when the size of x is large. So that means the y values are much larger when x value is larger. The variation in y is much larger when x value is large. So in that case, if we take logarithm of y, then usually the variation gets smaller. Okay. So suppose the x and y has a positive relationship. Original graph is, I think actually I have shown the original graph, but the original graph is like this. Variation is larger when x and y gets larger. If we take logarithm, so these numbers gets closer. So that is one possible remedy. So we have to take logarithm of y. But the relationship looks linear in the previous, scatter plot. So that means also we have to take the logarithm of x. And around 3000, we have many negative errors. So maybe some special reasons. So we have to look into observations with around 3000. And yeah, maybe we have to separate the data set into two groups, or we have to do some more additional statistical method. So that is how to interpret residuals and how to see if the residuals are independent. And finally, the QQ plot. So now we have checked whether epsilon I actually errors are IID. So another assumption is epsilon I is normal 0 sigma square. So what is this, how to check this normality of epsilon? And then we can use QQ plot. So basically the residuals, using residuals, this is theoretical quantile of epsilon I, and this is observed epsilon I hat. Then if this follows almost straight line like this, then this is normal. But in this case, maybe we have few observations extreme. Maybe it's not too bad, but the slightly epsilon hat slightly have more outliers. Yeah, so by looking at QQ plot, then we can see whether normal assumption is satisfied. And yeah, usually it's hard to solve the problem if this does not look straight line. But then maybe one case is if QQ plot is like this, we have some curvature, then this is theoretical, this is empirical. Then take log scale of y. So y into log of y. Then usually this kind of question solves. So we have to do some transformation of variable. Yeah, but if the curve is this complicated shape, usually it's hard to solve the problem of non-normal assumptions. So just our test result may have some problem, may have some limitations if the residuals are not following normal distribution. Okay, so now that we do some exercise, sorry, we only have a few minutes. I got the question, one more question. What's written on the y-axis on the last slide? Oh, here, the sample quantile. So this is QQ plot. So sample quantile. And the x-axis is theoretical quantile. Okay, so I will set up a room for exercise 7. Exercise 7 is for linear regression. So you can download it from Canvas. And we have 19 students minus 2, so 17 students, so maybe 4 rooms for 15 minutes. And I think we have to move 1 student to room 3. Okay, we start. Yeah, okay. So we don't have more time anymore. So I will upload the solutions for problem 2. And again, I will upload the midterm exam tomorrow probably. But you will have 1 week after the fall break is over. So you can either start or you can wait until the fall break ends. Yep. Okay, so if you don't have any questions, see you next week and have a good fall break.